Okay, can you all hear me?
Yes.
Okay, great. So today I'll be briefly talking about a phenomena we encountered in data processing, which is MS2 drift time offsets relative to the MS1 precursor in QTOF data processing. And so kind of a phenomena that is shown kind of on the right, where we have an increasing drift time difference, and we weren't sure if it was a function of the precursor to fragment mass to charge difference, but we also saw that it was a function of collision energy. And so kind of getting down to the understanding of this problem and the why of it, we have it deduced down to, it has to do with mass analyzers and pressure differences. And to kind of visualize this issue or thing to address is on the bottom right, we have drift profiles of MS1 and MS2. And so the peak apices are offset for the fragments relative to the MS1. And so this offset, we had it deduced onto being a function of collision energy and MS1 drift time. We also found another publication that kind of references this. And so in a lot of vendor software and other softwares, some people take a windowed approach to kind of capture this. And so we, instead of taking a windowed approach in our deconvolution, we first, to kind of get our handle on this problem, we thought, let's look at the simplest data we have, which is 2 mix. And so we have data collected for 2 mix at 5 collision energies times 5 replicates, and then for positive and negative mode. And so what we see here is that the offset of MS2 fragments to MS1 increases on average with voltage, and it's also different for positive mode and negative mode. And so to kind of address how can we shift our MS2 to apices to match more closely with MS1, we take the M and B of these lines per voltage and apply it to other data sets. And to kind of visualize what we've been doing here in our first approach is we can visualize it for a 2 mix ion that is at 601.98 mass to charge. And we tested it through a deconvolution in the Deimos package. And so what we see here in the top left is a drift time profiles for MS1 and MS2 for this unshifted or uncalibrated, I should say, raw data. And so we have these MS2 fragments that have the peaks that are offset from MS1. That would be, the properly attributed precursor. And we also have some co-drifting elements as well as noise. And so how do we kind of filter all this out to have better deconvolution results? And so for the MS1, plot center left, we have the true fragments and then what should get filtered out in deconvolution, as well as MS2 fragments and what should get filtered out. And so in a window-based approach, all of this may be attributed to the MS1. And we're trying to kind of cut down on what gets attributed in more properly assigned fragments. And so by taking the aforementioned on the left side, kind of shift correction factor and applying it to MS2 drift times, we now see that MS2 drift profiles are more, the apices are more properly aligned with the precursor. And so in the process of deconvolution, we kind of compare MS1 and MS2 profiles, and we take a cosine similarity, which gives us this matrix. And so now we can, for the precursor ion of interest, only take the highest scoring fragments and assign them here. So cosine scores like 970 to 990 or 999. And so kind of, visualizing how does this compare to Orbitrap shown on the bottom right. Everything that would get filtered out in this approach is no longer assigned, and that's kind of the light blue. And the ions that are considered true fragments and assigned to the precursor are bright blue. And then what shows up in Orbitrap is red on the bottom left. And so kind of, or in our second approach, you're thinking, what do we do for at voltages as shown for negative mode when we don't have unfragmented precursor to kind of generate the shift correction factor? So for like 1680 volt, how do we still address this issue? And so this kind of led us to our second approach, which is an affine matrix transform. And shown on the far left is a 2D profile of retention time versus drift time summed across the MZ dimension. And so what we've done is we have applied an affine transform to stretch, scale, and skew our data to minimize a cosine similarity function of A.ms2 and ms1. And so we make small modifications to A to minimize it such that we can minimize our function. And so kind of seeing this in action on the far right, we have our ms1 profile in blue, a light red is and a little bit to the left for the two red profiles is the ms2 before the shift, and the ms2 after the shift is the brighter red and a little bit to the right. And so this has worked really well for our data sets, and it's also been validated with our deconvolution, kind of using Orbitrap as a gut check. And all of this lives inside our Demos package over at P&L, developed under Tom. And I just want to thank our developers, our subject matter experts, experimentalists, and everyone who funded us.
Excellent. Thank you very much.